This recording is about nuclear chemistry. And so what you should guess from the name is nuclear chemistry. That's going to mean anything that has to do with the nucleus of the atom changing. And so with this video, I want you to think about the relationship between unstable nuclei and radioactive decay. And then we're going to specifically look at alpha, beta, and gamma radiation and look at those. What are they and how do they affect the mass and charge of particles? So we talked about neutrons before, and we talked about the fact that the number of neutrons that are in an atom will determine sort of the isotope of that element. And I also talked about before the fact that the job of a neutron is to sort of act as a kind of a cushion inside the nucleus, because remember that inside the nucleus it's really, really dense, and there are all of these protons that are being pushed together, more and more and more dense. And so because you're getting all those positive charges so close to each other, they're going to want to try to repel each other. And so the job of the neutron is to kind of end up holding the nucleus together, to get in there and cushion between those positive charges. So depending on sort of the ratio between protons and neutrons can sort of determine how sort of energetically favorable that combination is. So sometimes I might even say the word like how comfortable the atom is with that combination of protons and neutrons. And so if it turns out that there is an uncomfortable number of protons and neutrons, you end up with an unstable isotope. And that means that it's radioactive. And so how does it get stable? Well, it gets stable by releasing different types of particles and energy. And it will continue to do that until it has achieved a state that is energetically favorable. And things that go through that process of radioactive decay are referred to as isotopes or radionuclides. Okay, so before we had talked about Ernest Rutherford, and Ernest Rutherford was one of those people who was really interested in radioactivity, and I'm sure that you have heard of Marie Curie. She was one of the first people to work with radioactivity, and so together with their work, they determined, that there are these emissions that come out of nuclei. And the three big ones that we are going to talk about are alpha decay, beta decay, and gamma ray. Okay, so we talked about alpha particles just briefly when we talked about Rutherford, because he said that Rutherford shot alpha particles at that gold foil in his experiment. So an alpha particle is exactly the same thing as a helium nucleus. So that means that it has two protons. Here's one, two protons, the red ones, and then the neutrons are the white ones. So if we wanted to know the mass of this thing, we would say that the mass of an alpha particle is 4 AMUs. So a general equation for the decay of a isotope by alpha decay looks like this. So I showed you before, we looked at this kind of isotope notation. So X here, that means any symbol for any element from the periodic table. A refers to the mass of that isotope, and then Z down here, that's the atomic number. Okay, so when that unstable atom breaks down, you get something new. In this case, we're just calling it Y. We're going to call it a slightly more stable atom. And then we get an alpha particle. So you can figure out what Y is by taking the Z number from the original, subtracting 2, and taking the mass number and subtracting 4. So you would then look at a new Z number on the periodic table to figure out what new element you have made. So an example of this would be something like radon. So radon is number 88 on the periodic table. It weighs 226, and you can see here this is a diagram showing that it breaks down into two things. I'm sorry, I think I got these confused. This is radium breaks down into radon. Sorry, got those two R's confused. So when radium breaks down to give us radon, you can see that the mass up here has gone from 226 to 222, and the atomic number has dropped from 88 to 86. So this is that same basic equation that I showed you before, and then this is putting the radium to radon decay in the same format. So you can see we started with a mass of 226, it drops by 4 to give us 222, and then we have the atomic number of 88, it drops to 86, and when that number of protons drops, we get a new element, because remember, the protons is what determines the identity of the element. So if you wanted to double check this, you could say, okay, here's the alpha particle. So we have 4 plus 222 equals 226, and then 2 plus 86 equals 88. So this just shows you that even if you know then that radon breaks down by an alpha particle, we're going to do the same sort of math here again, and we can figure out what this in between would be. So if radon lost a mass of 4, we'd end up with 218. And if it lost 2 protons, we'd end up at 84. So we'd look on the periodic table, find number 84, and we would find out that that is in fact polonium. So you can also use this same idea where if we knew that thorium was the breakdown product of some radionuclide, but we didn't know what it came from, we could work backwards to figure out what X is. All we would have to do is that math. 4 plus 230 would have to be something that was 234, and 2 plus 90 would be 92, which is of course uranium. Okay, next kind of radioactive decay I want to talk about is beta decay. So what beta decay is a fast-moving beta particle, it's a fast-moving electron which is emitted from the nucleus of an atom. Now, if we listen to that statement again, so it's an electron which is emitted from the nucleus. So you should be thinking right now, what is an electron doing in the nucleus? Because you should know enough about atomic structure to know that there are no electrons in the nucleus. So how did it get in there anyway? So what happens during beta decay is a neutron is actually going to break apart. And what happens when that neutron breaks apart? So here's our neutron. It has a mass of 1 and a charge of 0. It's going to break apart into a proton, which still weighs 1, as a charge of +1. And then this over here is the symbol for our beta particle. It has a mass of 0 and a charge of -1. So again, if you look, you can add those together. And the reason that this occurs is the same reason that we would have alpha decay. Because remember, the whole point is trying to find a ratio of protons to neutrons that is energetically stable and favorable for the atom. Okay, so when you have beta decay, the nucleus is going to have 1 less neutron, but an extra proton. So you have to think about what's that going to do to our A and our Z numbers and our isotope notation. Well, if the mass is not changing because the neutron just changed into a proton, then the mass number is going to stay the same. But the atomic number is going to go up by 1. Why? Well, because that neutron changed into a proton. So we now have 1 more proton. So beta decay, mass stays the same, atomic number goes up by 1. So here's an example of something that decays by beta. So this is polonium. And polonium is number 84. It weighs 218. So if this is going to break down by a beta particle, we're going to expect this mass of 218 has to stay the same. But remember that the 84 is going to go up by 1. So down here's our beta particle. And then here is our new element that's generated. Again, the mass stays the same, 218, and our atomic number went up by 1, 85. So we now have a new element, At, that is astatine. So here is the general equation for beta decay. So here is our XAZ isotope form. It is going to break down by beta, and we're going to get the same mass, but our Z goes up by 1. So again, here is the polonium to, I think this is a mistake here. This should be astatine here. So this should be 218 and 85, and this should be At plus a beta particle. So again, here is looking at another thing, thorium. Thorium is number 90, and it has a mass of 234. It's going to break down by a beta particle. And so when that happens, if we look down here, thorium is going to go to protactinium. The mass stays the same, and the atomic number goes up by 1. And we could also use that same format to figure out what our original isotope was. So if we know that we have some lead 210 and a beta particle, we can figure out what the original X must have been, because we know that the mass is going to stay the same and that the Z has to go down by 1. And so if we do that, then we see that we would get thallium 210. And how I'm determining what this element is by looking at how many protons it has and then comparing that to the periodic table and getting the symbol from there. Okay, and the last kind of radioactivity that I want to talk about is something called gamma decay. So gamma decay isn't like a charged particle. It's not like an alpha or a beta particle. What it actually is just high frequency electromagnetic radiation. And if you're like, okay, well, what is electromagnetic radiation? Well, if you look down here, this is the whole electromagnetic spectrum. So the visible light part, sometimes we make it look bigger like this just so we can see what part of it that we actually are able to see with the human eye. But the electromagnetic spectrum is made up of a lot more different types of waves that we aren't able to see. So if you go beyond the purples that we can see, you get ultraviolet rays, and then beyond that is X-rays, and then beyond that are gamma rays. So things down on this end tend to be very high energy and very penetrating. That means that they can go through lots of things. Particularly, they're very high energy and can go through humans. So gamma rays are a very dangerous type of radioactive energy because they can do a lot of harm to humans through damaging DNA. And if we look at the far end of the spectrum, beyond red is infrared, and then we have radar, and then down at the other end we have AM radio, which are very large wavelength. They don't have a lot of energy, and they travel for really great distances. Okay, so that's the electromagnetic spectrum. So where is this energy coming from? Well, when an isotope is decaying by alpha or beta particles, sometimes that's not enough in order for the nucleus to feel that's this pretend comfort that I've been talking about. So in order to sort of finish the radioactive decay part, it also gives off a large amount of energy, and that leads the newly generated isotope to be more stable. So you can get gamma rays with both alpha and beta particles. It's just an additional kind of radioactivity. So I wanted to tell you just a little bit about how you detect radioactivity. And the thing I want to talk about is called a dosimeter. And this might be something that you would see on maybe like an X-ray technician, or maybe someone who works in the hospital who works with radiation therapy for someone with cancer. Or you might wear this if you worked in a lab that worked with radioactivity. So a dosimeter, what it basically does is compares sort of the normal background dose of radioactivity that you get compared to extra radioactivity that you might be exposed to at your job. So you might say, wait a minute, what's background radioactivity? But if we go back just one page quickly, so all these things down here, gamma rays, X-rays, ultraviolet rays, we are coming in contact with these things every time you go outside. The cosmic rays from space are different energy waves that every time you go outside, you come in contact with. So that is a small amount of radiation. And so that's called the background amount. So when you work in a place with radioactivity, they try to tell a difference between how much is normal, and then if you happen to have an exposure to an amount of radioactivity due to your work. So the other thing, some of you guys may have picked this up when you were doing your research for your project. This thing is called a Geiger counter, and this was actually created by Hans Geiger. And that name should be ringing a bell because he was the guy who worked with Ernest Rutherford and did the work on the gold foil experiment. So the difference between a dosimeter and a Geiger counter is sort of a dosimeter is this little thing you clip on your clothes, you walk around with it, and it's not really meant to measure an amount of radioactivity. Where a Geiger counter has kind of a little wand thing attached to it, and it allows you to sort of keep track of where the radioactivity is. Because you have to remember that radioactivity is colorless and odorless, and so there's really no way to see it. So the Geiger counter allows you to see where your radioactivity is. And of course, you have to be really careful when you are working with radioactivity. You need to keep track of where it is because you don't want to, of course, have an accidental exposure. So that's all that I have for now on radioactivity, and I will make another video to talk about half-life and carbon-14